All right, welcome to class, everybody. We are going to be working on Module 4 today. I do have the PowerPoint queued up here on my other screen. I'm just going to slide it on over. Full screen with it. And as normal, I am not, um, going in slideshow mode. I, personally dislike that very much, when teachers do that to me. So this is a lot more flexible for coding. I also like to see what's coming up ahead, and you guys might too. Just remember, if you are following along in the PowerPoint, that PowerPoint has a little notes feature. I don't know if you guys know this or not. Uh, it's kind of like the IT geek in me to point it out. But they have this little notes thing that you can turn on this panel down here, and you can type stuff in and save it, by the way, right? Now, sometimes you'll get a PowerPoint from somebody and the notes are already packed with information, usually for the presenter. But it is also it's a great way to take notes, really. Once again, methods for capturing information and how you proceed. The agenda for tonight is as follows, and it's really for the whole module. My hope is, and I'm looking at the number of slides here, there's a lot of slides. I don't know if I'll hit them all. I'll try. It's kind of my hope. We are going to look at increment and decrement operators. These are, if you've ever heard of the programming language C++, these originate from that language, by the way, and kind of have been around a long time. But not all languages utilize them. Predominantly, what we call the C-style languages of C, and C# is one of those, do use them, and it's a normal tool. So we'll look at how those operate, and then we'll look at the two major types of looping structures that we have available in C#, which are the while loops and the for loops. Interestingly, both of those loop types have multiple subtypes that operate. So, for example, the while loop's got the do while, and then there's a regular while, and then the for loop's got a for loop, and a for each loop, and a for in loop, and it kind of goes deep. We'll also look at the concept of taking a loop and putting it inside of a loop, novel, and then also the special commands of break and continue, which are often used with loops. We already saw the break command with a switch statement, right? Where you can hit a case within the switch and you need to break out. Otherwise, you keep processing, and that's not often what you want. We will have some of the loop topics, most notably the for each loop, which is kind of a special type of, I think of it as an automatic loop that we'll talk about next module, by the way. But a lot here to kind of wrap your head around. The thing that I will say that before we dig in here is, we learned about the three major strategies for solving logical programming problems, one being sequence, step by step. And I know I repeat this every week, but it is important. And then we also learned basically decision or selection statements. Those are if statements. Switch case statements are also in that category. And then now we're finally hitting that last major conceptual structure, which is repetition or looping. And it is a really important structure. And often in coding and in life, there's tasks that you have to perform over and over again until you get to that successful state. I do love this slide here and the photograph of this computer in the background, because there was a so John, I see you're laughing, right? So it's like your gray hairs are becoming evidence, or right, yeah, you can go ahead and say what you want to say.
I started on that at UW Milwaukee and JobDex. My first job actually ran punch cards.
Oh wow, okay. And that's what's kind of fascinating. This is actually an old Commodore computer, and this was considered a kind of high-end one because it had the cassette player built in rather than as an add-on. And if you didn't know, back then we didn't have storage in our computers, right? If you were lucky, you had a floppy drive. We didn't have hard drives, so when we would load up an operating system to run it, we'd load it off of cassette or store our programs on cassette and read them off of cassette. It was, a very primitive version of a tape drive, but hey, man, that's how primitive things used to be. It's funny, John, that you kind of mentioned that, right? Because I saw your face kind of light up with that slide too, because I come from that era of computing as well. I never owned a Commodore. I started with actually an Apple, and I was fortunate because it came with all sorts of gadgets when I bought it because it was a hand-me-down. But I learned pretty much the hard way from scratch. All right, let's ignore the computer history part now, and let's actually get into some material. And we are going to learn what the word increment means. And I guess, maybe you've never really thought about this, but normally when I think of the word increment, I think of like doing things like in little bits and pieces, right? Like, do that incrementally, you know. And really, when you stop and analyze the actual word, what the word increment means is to increase. And it comes from that word, right? That's where increment originates from, is from the word increase. So when we are doing an increment in programming, typically we mean to increase a value by one. Now, this is a really common operation in computing because it's the most fundamental of math operations. And why we even come up with it is, because we think about numbers and we think about like counting on our fingers and we go like one, two. We just incremented by one. Now we're incrementing by another, and it's three, right? And it's very common. In a coding format, we often will use the syntax like this. So if we're storing a value in number, we might take that number, add one to it, and the result of that calculation then gets stored on the left side of that equal sign. So number plus one gets stored back in number. Or what we've learned already is you can use this combination operator where you can say plus equals, which does exactly the same thing. And this was really considered like huge advancement in programming because then it saved you the hassle of writing this extra word, which is such a huge hassle, right? It can be actually, right? And so I kind of like joke about it. But in the C++ programming language, when that was introduced, increments were done so routinely in that language, like when you're like adding something to a value, you got a counter running or something like that. They came up with even a more shortcut way to do it, right? Which is the plus plus operator. And that's why we call the language C plus plus. And by the way, C sharp's kind of a variant of it in that if you look at the hash mark operator, it's kind of like plus plus double, right? Because it's like the hash mark can be broken down into 4 plus signs if you really think about it, right? So it's kind of a hack sort of on that. But basically, this does the same thing that the statements here do, is they add one to whatever number is. And see how nice and short and simple that is? I mean, it's just one little statement. You say plus plus, it just means I'm incrementing it by one. It's so common. Why don't we just come up with a special way to do it? And that's exactly what they did, right? Now, they'd call this a unary operator because it's one operand. Well, it's really two symbols, but it's one combined thing that makes one symbol. That means to increment. Now, interestingly, there's a decrement also. So we can also subtract, so we can count down from things. That's pretty common too. So we can go number minus one, put it in number, or we can say number minus equals one, same difference. And as you might guess, there's a decrement also, which subtracts from the number automatically. So we say number minus minus, right? So that does the same thing. It reduces whatever's in number by one and stores it back in number. Pretty clever. This is also what they call a unary operator. Now, fascinatingly, and we're going to like do a little bit of testing on this here in just a moment, there's kind of two different versions of these. This is kind of where the mind bender comes in. And I think in all the languages that support this, plus plus or minus minus, all operate in this fashion because we have what we call a postfix version, which is the one that we almost always use in every situation. But there's also a prefix version too. And it's all about how it operates. And this is really, really weird, right? And the only way I can really explain it is to show you. But basically, the number plus plus and plus plus number will yield the exact same result when it's a standalone statement like that. Both of them will add one to number. But if I'm operating in a mode where I'm outputting the number, I might get different results because of how the language processes the code and then puts things on the screen, right? And I like the statement here. It says, if used in isolation, there's no difference. All that matters is when plus plus or minus minus is combined with other operations. So in other words, if I'm combining the plus plus with an output, it might change the output as to when it happens. All right, so I think what would be really wise to do at this point, let's create a blank application. So I have Visual Studio all poised here. And I'm just going to write this generic console app here so we can just get rolling. Sure, console app 4 is beautiful for doing demos. Let's just get that code up and running. So you guys should do the same if you want to follow along. If not, that's okay too. You can just watch. No harm done there. Now I'm going to get rid of the comment here. I am going to zoom in just ever so slightly so you guys can see my screen just fine. And I'm going to try these operations that they're talking about. So I'm going to grab all of this code here and just, no, I guess I can get rid of that too then, and just paste it in. Now, I'm going to kind of proceed sort of like one line at a time here. Okay, so this is not Python again. You guys catch me again on this? All right. So let's do a little bit of experimenting with these console write lines. All right. So the first thing I'm going to do is we're presetting this to 4. I'm going to output it so we can kind of guess. And this is kind of what I ask you to do is maybe guess at the output. So this should output 4 for sure, right? In fact, we know with high degree of certainty that's going to happen. But the second one should display what?
Five.
Display 5. All right, so that's our guess, 5. Should we run it and test it? Sure. Let's do that. Let's run it. Not what you guys expected, is it? Yeah. So here's what's going on. When it's combined with another statement, the other statement or operation will read number literally as it is. Now, if I were to output this again, so if I just repeated line 4, and I think this is the best way to show this, by the way, otherwise you never really get the conception of it. If I run it now, that third output should be 5, because really what's happening is it's console right lining in order. It does the output, then it increments, right? So I really can't see that until after, right? So what this tells you is that when I put the increment in front of the number, this is why we have 2 different versions, then I can add the increment first and then display the number. Right, so let's run it. So really the output here is 4, right? And then the output here finally was 5. So therefore the output here should be 6, correct? You guys with me? Yeah, the output here should be 6 because now it's adding the value to 4. So I'm just going to put that guess in there. Let's run it and see. And there you go. So we got 4, 4, 5, 6. Kind of another helpful little tip here. And I don't know if you guys knew this about the console, because it's basically a command line for Windows. It is possible to actually edit, like if you don't like your font look, colors, and because some of you are probably running it and going, how come his looks all cool and green on black or whatever, right? And that's because I've changed mine, right? But you can actually come in here and change your fonts. You can also make these panels transparent, by the way, if you wish. You change your font size. I'm at 18 point right now. Maybe I'll go up to 20, right? Just to make your code reading experience a little more pleasant, I guess. But you guys can tweak that, and you can even change the font style if you wish. All right, so that's an example of how postfix and prefix mode works on this increment and decrement. So now we get the like follow up on it. So what happens first? The output of the number happens first. The increment happens after, so we don't see it in this right line. That's the thing. So just remember that, just in case you're quizzed on that. And if we put it in prefix mode, we would do that in anticipation of something being added so we could output it correctly. So normally we're not really using prefix mode. Very often, by the way, when we're doing these types of operations, I might do number plus plus as a standalone. I don't have to assign it to anything or make it part of a right line, right? And then we take a look at the output in the aftermath, right? So I can just simply right line and output it. Once again, if I run it, take a look, right? Increments before. Now, if I change this and increment before, is that going to change this final output? No, right? Because the operation happens, it's already done by the time it gets there. Right. Let's run it just to make sure, right? If it gives me a different value, then I'll be corrected. But if it's a standalone statement, it doesn't matter. It does basically the same thing. So the normal way really is number plus plus, right? If I go plus plus number, really kind of the only functional reason to do that is it's being used in combination. That's why. All right. So hopefully that clarifies it, but that's how we do increments, decrements, and plus plus and minus minus operators. Very common in all C-style languages. Now we're going to move on to the concept of loops. And, we are going to look at, basically 4 different major loop structures here in C#. And we're going to do it basically in the order shown here. We are going to start with the while loop. And, basically what a loop does, and I think I mentioned this as we started, is a loop takes a block of code and repeats it until we determine basically when to stop it, or we'll talk about all that. But generally speaking, we like to have a loop that operates a finite number of times with intent. Loops, however, can be set to do some really cool things that we haven't been able to do so far in our programs. I want you to think about this. Like the program that I just created to demonstrate the plus plus and the increment and the postfix and prefix approaches. Like every time I wanted to test it, I'd have to stop the program running, close the console window, go back to Visual Studio, hit the run button again to make it run to try the next thing, right? Wouldn't it be so much more handy if I could just have the program keep running until I wanted it to stop, right? Now that's the normal way we operate software, right? And but you can't really teach people how to do that until you learn about loops. So looping has a huge place in programming. One of the most fundamental is to keep a program running so people can keep using it rather than having to relaunch it like every time. So think about like the stuff we were doing last week, where you'd maybe type in a different value for figuring out your gift card or whatever. And wouldn't it be nice if we could have just put the whole thing in a big loop and then try it again with a different value and not have to restart the program? Absolutely. Right. That would be very, very useful. Very useful. All right. Let's take a look at, first of all, the logic of how a while loop operates. So this is the first one that we're going to learn. In many ways, it's kind of like an if statement. All right, so when we would represent it in a flow chart, we still use the diamond shape. And the reason is we will have a Boolean expression, in other words, a true false piece of logic that we will check going into the loop to make sure that it operates, right? So if the condition registers true, so take a look at this. We come into the expression, let's say it expresses as true. We'll go down and we'll execute whatever code's inside the loop. And when that code's done, it goes back up to the top of the loop. checks the condition, like checking the if statement again. And then if it's still true, it keeps executing as long as that condition is true. Um, Now, if it happens to be false at any point, either while the loop is running or coming into it, it just won't operate at all. So that's kind of the visual approach of the branch. So it will branch true and false, but the true branch will always come back up. I do want you to notice that, in this drawing here, I might actually eliminate this little line to help make it a little clearer. But there are situations when you can actually branch out from inside the statements too. That's what the break and continue things are, but we'll get to that in a little bit. But generally speaking, we test the condition. If true, we run the code. We go back, test the condition again. If true, we run the code, test the condition again. Get the feel of this? It repeats, right? And then when it finally registers false, we will pop out of the loop, right? So here it is in code. So I want you to notice that we have the keyword is while to set up the loop. There is a set of curly brackets to encapsulate the repeating code. And then just like an if statement, inside of parentheses, we have a Boolean expression that tests for some version of true false in order to get the loop to run. This must be true in order for the loop to execute at all. So what we're doing here, notice, is we're checking a variable called number above the loop, and this is really key. We are presetting it to force the loop to start running. If this number was 11, this would be false. The loop would never run. Right. So what I'd like to do is I do want to just take this code as is, and you can do the same thing if you're following along, and execute it here in Visual Studio. Right. I'm just going to hit the run button on this. This is pretty simplistic, but it's always nice to see the software run. And let's kind of trace through what just happened, because it happened in an instant. Like, you didn't even have a chance to think about it. So we have numbers set to 1. So it comes in here. This is 1. Is 1 less than or equal to 5? Yes. So we output hello, and then we increment number. So number now is 2. Come back up. Is 2 less than 5? Yes. Say hello. Increment again. It's 3. Is 3 less than 5? Yes. Output hello again. Now it's 4, right? Increments up to 4. We finally get up to 5. Will the loop run? Yes, because it is less than or equal. So 5 would still trigger it to run. So we have 1, 2, 3, 4, 5 hellos. It increments again. It reaches 6. Comes back up here to check it. 6 is not less than or equal to 5. So now this is false. So it jumps out, skips the statements, goes to the last statement, and says that's all. I think what would be helpful, by the way, and this is kind of the goofy stuff I do when I'm teaching loops, because I think it's helpful, right? Is it's not a bad idea to sometimes just output the number to the screen to see where you're at in the loop. That's kind of helpful too, right? So if I run this again, now I'll get hello 1, just shows you the value that it currently is every time I hit the loop, right? And then really I could take that same statement and do that. Now sometimes when I'm coding, and I just kind of tell you this is just a practical tip or tool or whatever for the future when you guys are doing this professionally, that now functionally outputting the number really has no purpose here, right? Except for me as the programmer, it helps me to keep track of where I'm at and if it's working or not. And so I could just like put that in for now to see where I'm at. And then, when the program actually launches and runs and is used for real, I would get rid of it. But at least while I'm building, I can throw that little snippet in there just to see what I'm outputting and if it's outputting correctly. Just as simple as that. So that's just a handy little tip. Now, a couple little things that we're going to learn about this, right, is what if I set this to a value that the while loop never hits true? Well, that's pretty easy. It's not going to do anything, right? So if you intend that loop to run, you are presetting that value. This value that we use, in this case, number, we refer to it in a number of different ways. So like some people will call this the sentinel value. In other words, the one that we're looking out for to see if the loop will run. Other people will call it the loop control variable, right? So this is all terminology that you can kind of throw in there. Now, well, let's go back to the PowerPoint here. We'll probably hammer on these points all night long. So that was a nice little example to see how a while loop operates. Every time we step through a loop and we run it once, it's called an iteration. We are iterating code, right? So we hit that while loop. If we're in there and we run through all the statements, that's one iteration, one pass through. When we run it again, it's called reiteration, right? So you hear, like some of you may never use that word, but if you ever heard somebody, hey, I'm going to reiterate what I just said, it means I'm going to repeat it. But the single time it's done, it's called an iteration. Every time it goes through a single time, that's a single iteration of the code in the loop. Just terminology that programmers throw around to confuse people who aren't programmers, by the way. Right, but that's a really good one. Iteration is a thing. So each repetition of the loop is called an iteration. Right, the sample loop that we looked at performed 5 iterations. It did it 5 times, and then we can actually use what we call breakpoints to help us visualize loops. Now, I'm not like super huge on using breakpoints in code, but if you guys have ever done this, you can. For example, like my primitive way to kind of do a manual breakpoint is to basically output what the value of the sentinel value is as we're going through so I can see it. That's kind of my practical approach. But let's say you weren't doing this, right? You could actually hit this little thing in the margin here, and this is called a breakpoint, right? And what this does, this is really kind of goofy. Watch what happens when I run this. First of all, it runs the code. Oh, of course, this isn't going to run because we're never hitting the loop. Okay, never mind. That's not a good example. Let's switch that back to 1. All right. One more time. Let's try that again. And I like to have the console window down here at the bottom opened up a little bit too. All right, so let's hit the run. And notice what will happen here is, I do want to have this up on the screen. It hit this point in the program right before this code executed. So what a breakpoint does is it stops the code at this point before the line executes. All right, now you're going to say to yourself, why on earth would I want to do that? Okay, there's a reason, right? Look at the bottom left panel here. Nothing's happened on the screen yet, so that proves that the output statement didn't happen. But down here, we have like our little panel that shows my variables in the program and the current value of that variable at that point in time before this statement is executed. It's kind of handy, right? Kind of the programmatic way inside the IDE to set a way to check what your variables are set for. Now, we're doing really simple numbers. We're just counting up, right? Not a big deal. Easy to figure out. But what if every time you did this, it came up with some crazy calculation? Or maybe you have one thing that's controlling the loop and then a different variable coming up with some crazy value, and you want to see why your program's failing or succeeding or what value something is at a current point in time. We set these breakpoints, and all you have to do is click in the margin here, and it puts in basically a little stop sign is what it is. Now you will also notice, right, I can disable it by just clicking back over here, which I'm going to do. And then you'll notice here as well that as I hover in front of the line, it's telling you run execution to here, right? You'll also notice the play button up here is stuck and now it's in continue mode. So if I hit it again, right, really handy too. It tells you it did it in less than four or about 4 milliseconds were elapsed. And now it went through. I'm not seeing the console, so that's a little irritating, but it did one iteration. It added the number. You can see it went up to 2. It cycled back up, did the logic test, and it stopped right here again, waiting for me to continue. Kind of irritating, frankly, on a loop, right? But if you want to see what's happening in your program and you want to be able to stop it, breakpoints are kind of a way to do it. Okay, so let me talk a little bit about breakpoints. I removed it and see how easy it was to remove, but you can put those in your program at any point, right? If you're not sure, like, hey, what's the value of this at this point? Well, put in a breakpoint and find out. Can I put in multiple breakpoints? Sure, you can make it stop on every line of code if you want. Very irritating. I will tell you, historically, as a programmer, I've never been really big on using breakpoints, to test values. However, I also haven't had significant reasons to use them, in teaching, okay, well, I like to teach you guys how to use it. But when you set a breakpoint, you have this whole terminology that goes with it. There's like step into, step over, stop here, resume, all this kind of stuff that goes with. It is a handy thing, but the PowerPoint points it out, and I do think that it's useful for loops if you're just trying to latch on to what's going on. I also showed you my practical view on it, which is you could just simply do this to keep track of what the values are. Of course, you can't stop the loop from running at that point, right? But it is very handy. Breakpoints are handy, but you can also use practical programming tips like just adding in a line of code to output stuff to see where you're at, right? Generally speaking, I also tell people that when you're doing output to the screen for a user, being more verbose is better than being less verbose. I mean, don't you like it when you operate a piece of software and it's giving you more information you can even possibly use? Yeah, why not, right? Even if you're not using it, I'd rather have more than less. Right? Choose not to look at it. All right. So we asked the question here next. What happens to the value of number as the loop repeats? It increases. Why? Because we have that thing in there called the loop control variable, which is what I called it. This is also, once again, called a sentinel value, right, by others. And this is important because it is number that we are testing relative to a value to see if the loop runs. Now, read what it says. So number plus plus increases the number each time through, each iteration. Eventually, the statement will become false because we've increased so far that it's no longer true, and then the loop doesn't run. It stops repeating. We are in control. We were in control of it starting by setting this value where it was, and in control of it ending by making sure the value changes inside the loop. Right. So, and that's a really important aspect of this. If you're using a value to check, your loop control variable, if you want to eventually come out of that loop, that value's got to change somehow within that loop in order to pop out of the loop. Otherwise, you get into the situation called the infinite loop, which we're going to talk about in just a minute or two here. All right. Now, because we are checking the condition of the while loop at the beginning of the loop, before the loop starts, we call this type of a loop a pre-test loop. We are testing before we are looping. All right. Now, does that imply that there's a post-test loop? Yes. Right. Right. So we have the while loop and then its companion do while, which we'll see in a few moments also. But we test the expression first, then we do the statements. We pre-test, and then we run the code. Here's another problem, and we talked about this already. If the expression's initially false, right, and I just did that accidentally before I left it set to 11, the loop, I'm not going to say may never run, will never run, right? this loop will never run. The number will never be less than or equal to 0. So if your intent was to make it run, well, you have a flaw in your logic, right? This takes a little bit of practice to build these kind of statements, just like an if statement, really. So it's not that hard. We do have the situation, though, that if that loop control variable doesn't increment, there's kind of fun to test this theory, by the way. And it's pretty easy to do. So I'm going to take the code that I have. I'm going to comment out the increment. I'm going to get the loop to run. Okay, I'm just gonna do it, not say another word about it. Here you go. Now, what you can't tell right now is this is continuously generating the word hello, right? I can't even scroll fast enough to keep up with it. I don't know how many iterations it's doing. All right, so what happens if you get stuck with an infinite loop? Control C in a Windows environment or Command C on a Mac, by the way, will break a program that's stuck in an infinite loop. Yeah. That's a really good one to know. Just to prove to you that it is actually running, I'm going to uncomment this line so we can see the numbers increment. I'm going to run it again. And so we have this infinite loop. There you go. Now, interestingly, keep in mind, I don't know how it's carrying across on Zoom, but this is very interestingly animated here for me. Are you noticing that the number's not changing? Oh yeah, right, because we told it not to change. It's always going to be 1, but you can kind of see hello flashing, which, I mean, this is just going and going and going and going and going. It's so fun to demonstrate infinite loops. Yeah, the only way to stop it, unfortunately, is Control C. And that's kind of like a hard stop, by the way, right? Not an elegant one. You really do not want to write code that gets stuck like that unintentionally. So the increment becomes critical to prevent an infinite loop. Now, there are those circumstances that an infinite loop is actually useful, right? Now, you might not think about this, right? So like normally you write like these simple programs like we're writing, and you're like, man, I don't want this program to run forever, right? But think of the scenario where you boot up your computer, and then once you get booted up, you can move your mouse across the screen like I'm doing right now. Somewhere inside of Windows or the Mac OS or the Linux OS distro that you're using, there's a program that continuously monitors the position of my mouse on the screen, what it's doing, and if I'm clicking or not clicking. That's operating in a loop. By the way, an infinite loop that does not stop until Windows is shut down. Right? That mouse stays on the screen the whole time. And the thing that monitors the mouse position on the screen waiting for an action is an infinite loop. So there are actually uses for infinite loops. But obviously, when I hit the shutdown command in Windows, whatever controls that mouse is, I don't know if it's a Control C, but whatever, it sends a terminate command and then we're out, right? But there are times where an infinite loop is actually kind of useful. And you think about it from a graphical user interface and in mouse interactions, it makes a whole lot of sense. When is it stopping tracking my mouse? Never. When my operating system's up, it's always monitoring my mouse position, always. And if you're on a mobile phone, it's always monitoring the touch screen for interactions, right? Same kind of thing. All right. So there are actually places for infinite loops. They're not considered ideal though, right? So like if you kind of look at the example here, and I think we kind of mentioned this already. Yeah, so don't put a semicolon here. That's the grand tip here, just like an if statement. Um, you know, that's a no-no. That won't work, right? I don't think it would like fail to compile, but it won't operate the way you want for sure. Now, a while loop like an if statement, if you only have one statement inside, you don't need the curly brackets. However, right, so if I ran this, what would happen? It would run infinitely. It would just keep printing hello, right? Because it would never hit the increment. So recommendation, just like with if statements, and this is a big recommendation, always put the curly brackets in, even if you have one statement. That would be my recommendation, because a while loop requires the loop control variable to be preset in order for it to run. If you're only doing one action in here, the only action you can really do is to increment. And then what's the point of the loop, right? So curly, I mean, it's a logical thing, right? The curly brackets really are pretty necessary here. All right. One spot where while loops in particular are very useful is when we are running, console programs or lots of kind of programs that we are expecting user input in order to operate a certain block of code and maybe continue operating the code. So let's take a look at this example. So here we're reading in some sort of a value and we're checking, is the value that the user just entered, is it invalid? And think about how this is being asked. So enter number 1 through 5, 7. That would be invalid input. Okay, so then we would put an error message on the screen, and then we would ask them again to input the same information. Or maybe a better example would be enter your password. If the passwords don't match, okay, you know what? Wrong password, try again. Now we might have another thing in there, right? You don't want to keep allowing people to enter the wrong password. Eventually, they'll get after an infinite number of tries, they'll finally figure it out, right? If you try every possible combination of letters and numbers. So usually you might actually put a counter in there and say maybe 3 attempts or 10 attempts, and then you get locked out, right? So this is very common, right, for user interfaces. Like we've had these situations already in a program where we're asking somebody, hey, enter an integer, and they enter a letter, right? So if the input's invalid, now we can test for it and ask them to put in something valid. So rather than just stop the program or crash the program, we can actually set up mechanisms. Now, the very first time we read the information in, right, and they're talking about this initial value being read in, we call that the priming read, right? So we'll put a message on the screen, we'll do the prompt, we'll capture the information, we'll store it inside a variable or whatever, and then we'll go into the structure, right? Now that age is set, we can test for it, test its condition to see if we want to run the loop. Okay, so when we do the prompt before the loop, we are still setting a loop control variable, but we call this the priming read. Like we're setting up the thing to work, and so we're feeding it information. We're going to check to see if it's valid, and if it's valid, we'll run the loop. If not, then we won't. But then once we're failing at it, so this would be the way that we check, right? So we'll say invalid entry. So if the age happened to be less than 0 or greater than 150, right? I don't know if anybody's ever been that old. Then we'll put a message on the screen. We'll say invalid entry, enter your age. We'll give them another chance. And we'll keep prompting them in this situation until they enter a number that's in between 0 and 150. That's how you would pop out of this loop. Now, we could test this if you want, and I think that's probably not a bad idea. So let's try this. Let's take the priming read. And this is why I think this is really helpful to test this stuff like this, right? So we're going to prompt them to enter their age, and then I'm going to go to the next slide and grab this code like that. And just to make sure that we're done, I'm going to do another console write line here. And then I'm just going to put a silly message on the screen. Okay, done. And just so that we know we're done. Little message. Let's run this. So here comes the run. So enter your age. All right, I'm -1. All right, I happen to be 189. No good. All right, we'll put something in range, and then we're done. Um, so this concept, right, and this is really very, very useful. By the way, in order to like force people to answer a way that works, this is one technique that we can use. This prompt, we call it the priming read, right? So we're priming the user basically to get the loop to run. If, of course, they enter something appropriate, it would never hit this invalid entry thing ever, right? So they would never see the invalid message. And then we can just go on and process that information as we would. So very common with user interfaces that when we prompt somebody for a certain type of information, the information is incorrect, we can ask them to enter it again. Let's go ahead and terminate that. So that's the priming read. Right. I think this is a really good spot to take a short break, you guys. So let's do that because we've been going for a bit now. All right, we're back from break and we're going to move on to our next topic here, which is do while loops. And very similar to a while loop, by the way, but it operates a little bit differently. What's interesting about this style of loop is a do while loop will execute its code at least once. That's kind of the main difference with a do while loop. And you know, the little bullet points here on the slide say it looks like an inverted while loop. So in other words, the statements inside the loop will execute whatever they are, then we'll test the logic. If it's true, we come back and we do the statements again and we keep going, right, until it tests false, and then we pop out. But no matter what, it will execute the statements inside the loop at least once, right? So this is kind of a different type of approach. And what's kind of nice about this is we can enter the loop with the loop control variable not, set to trigger it, but we'll still execute the code once. And I think that is actually pretty helpful in some circumstances. Now, if you look at it in a code fashion, look at the syntax and how this is different. We still use the keyword while with the Boolean logic test, but that's at the end. And notice there's a semicolon there at the end, right? And I like the arrow there to point it out. But we use a do keyword at the beginning. The code, so all this code will execute no matter what. Then we'll check the logic and maybe repeat, right? And you know what? Let's give it a try. Right, let's drop it into Visual Studio and actually try it. So here comes the example. And let's read through the code before we hit run just to make sure that we're understanding what it's doing. And we have numbers preset to 1. Code will start. It'll output hello. It'll increment that to 2. It'll test. 2 is less than or equal to 5, and it'll run again. And it'll keep running until it hits 6. And then we get our final little message. Let's try it. Right. Notice gave us the exact same output as the while loop, the first one that we tried, right? We still have 5 hellos on the screen. So what's the difference? Well, the one difference is, and this is really important, if I did set this to 11 to make it basically false, here's the difference. The loop executes at least once and then does not do it again because there's no condition set to prevent it. The condition is checked at the end, not at the beginning. All right, so that should be pretty clear, I'm hoping, for all of you. So therefore, we do call this a post-test loop. And, this can be very useful. There's situational reasons why this would be a better loop to use, right? If you have a reason, and I'm just going to kind of give you a real practical one. In the scenario that we had before where we did a priming read, right? And then we're trying to make sure people don't put in the wrong information. We can set up a scenario where, the priming read actually happens inside of a loop. But would that make any sense? No, it wouldn't make any sense for that situation. But we can ensure that at least the block of code operates at least once. And I think that's pretty helpful, actually, right, in some situations. I think we said that plenty. Now we're going to move on to the for loop, which is, I'm going to say, at least from my experience, like once programmers learn how to use loops, all of them have their situations where they're optimal. But if programmers have like a go-to loop that they go to first, usually the for loop tends to be it, because it has some special features to it that make it kind of an optimal choice for being the go-to, in most looping types of situations. So first thing that we look at here is, loops that execute as long as the condition is true. So like that's the while loop or the do while loop. And so, for example, here they're using the example, a user keeps responding yes at continue prompts, so yes, no, sure, yes, continue, right? We'll just keep running, right? So we don't know how many times it's going to run, right? So in a loop like that, if a user is interacting with the loop that keeps it running, we have no idea how long that loop is going to run. That could be a good thing. That could be a bad thing. It's really very situational. I would think if you're setting it up that way, there's a reason, right? And I don't know, play again? Yes. Play again? Yes. More pizza? Yes. Or whatever the question is. Now, the difference with the for loop, though, is we have control as the programmer as to exactly how many times it runs based on how we set it up. So, for example, if I want to run a loop, so it says enter sales data for 7 days in a week, I can preset my loop to run 7 times and then finish, because, hey, you know what? I only need it to run 7 times. Why? Because that's how many days are in a week. So, and if it was you're looking at 5 business days, well, you can set it for 5, and it's just a matter of changing a couple little aspects of how the loop is put together, right? Now, the reality is, and I'll reinforce this, when you learn how to use loops, you can write code logic to make any type of loop really do the same kind of action. So I can set up a while loop to do the same thing as a do while and the same thing as a for loop if I engineer it carefully. However, while and do whiles are more prone to errors when you try to do that. When we're trying to do count controlled loops, like a specific number of iterations, the for loop is really the tool of choice. And part of it is because the expression of creating it is much more simplistic and concise. It's more code compact than a while loop or a do while loop can be. So let's take a look at this example here. So take a look at the while loop versus a for loop that does exactly the same thing. Now, the way that this is expressed here, and I'm going to just say this out loud, is not very space efficient, because the for loop statement is split over 3 lines, and it is not how programmers write it, by the way. I'm only doing this, or we're only doing this here, to kind of drive home the point that the initial declaration of a for loop contains within it multiple statements, just so that they're clear that they're multiple statements. And you will notice semicolons in the mix here. So first of all, let's take a look at the while loop and take a look at the fact that we have to set the loop control variable before the loop is declared. So we have to know going in that we're going to run a loop. We're going to be looking for this value, so we better set it up here. Then we test for that value and execute the code, making sure inside to increment that value so that eventually we can jump out, right? So we're presetting the value, testing for it, and then incrementing. what the for loop does is it takes that initial setting and puts it inside the for loop, right? And normally, like when I look at a for loop, these three are on the same line, right? So we are setting an integer variable inside the for loop. That's going to be our counter or our loop control variable. Then we're doing the logic test in the middle expression. And the third expression is the increment that we're going to use so that the increment doesn't have to happen inside the loop. It just happens automatically in the structure. So here's what I'm going to do. I'm going to take this for loop code now. Let's go over to Visual Studio and try it. And I think that's helpful. I'm just going to paste it in. And then I'm going to express it in the way that I'm more comfortable. And really, this is kind of the formal way for doing a for loop. And you can see how that approach, right? And I'll just move it down a little bit so it's easier to see. All three of those expressions are in one set of parentheses. So I'm setting the loop control variable, I'm testing the logic, and I'm doing the increment here. So I don't have to do any of it before or internally for the loop. What's nice about this, if I'm starting at 0, right, how many times is this loop going to run without, actually, how many times is it going to generate X? How many X's is it putting on the screen? Right. Well, this is where like you have to kind of do like what we call step through logic, right? So we start at 0, so it's going to output. It's going to start at 0. Is 0 less than 5? Yes. It'll output an X. We'll jump up to 1, 2, 3, 4, 5. I'm counting 6 iterations here, right? When it gets to 5, it'll stop. So I'll put 5x's. Let's see if that's true. There we go. 5x's right there on the screen. Kind of interesting, right? Now, fascinatingly, there's a bunch of different things you can control about this, which is why programmers love the syntax. And now you're seeing it more written out this way. I have seen programmers who write it out where those statements are spread out like that, and you can do that and it doesn't fail. But the important thing is there are those semicolons in here because these really are separate programming statements. That's just the parameters that you send into a for structure. Loop control variable, logic test, and increment. And I do think it's important to note also that in this situation, we're incrementing, but you could also decrement too. You could do a minus minus here if you want. And this increment is in the form of the plus plus. Could I also say number plus equals 1? Well, you could try it. Actually, you can do all sorts of fancy statements here. Most commonly seen, though, is plus plus and minus minus. Right? But it is possible to do other things too. But generally speaking, increment or decrement in this position, logic test, loop control variable. And that is the basic structure of a for loop. Right? So just kind of a review, right? You got my way of saying it. So we call this formally the initialization expression, right? But it is setting the loop control variable or the sentinel value, if you will. You can see the efficiency. I don't have a separate line of code somewhere else. And with a while loop, I mean, the examples we've seen, the loop control variable set directly above it, right? But what if it wasn't? What if it was set like 500 lines up? You want to go hunting for it? Sometimes that happens in code, right? So it's really kind of nice that it's right inside the loop. So you can see it right there. Now, I will mention that here we're actually formally declaring a variable with its data type. I mean, could we have declared number somewhere else and just say number equals 0? Or just say number? Yeah, you could do that too, by the way. More common to do it this way, though. Then we test the expression. So same true false logic, Boolean expressions. They can get complicated if you want, but usually we keep them pretty simple based around the loop control variable. And then finally, we do some sort of a change to that loop control variable in order to make sure we pop out of the loop, right? The um, the graphical view of this in terms of like how we kind of process things, right? Is we come in, we assign 0 to number, we go in if the number is less than 5, which is going to be because we set it, right? It should be, hopefully. We will do the work. The increment still happens the same way. So in terms of like the flow chart of this, it's not really that much different than what we saw before. But the fact that we are kind of hot wiring this all into one statement is really the major difference. And it does become, in many ways, kind of the preferred loop for most programmers. Yeah. Now, the interesting thing is, if you're wondering, right, is this a pre-test or post-test? Technically, it's a pre-test loop. The checking happens before we step into the code. So it is possible that you could write the code like here, and you could set it up so it never runs. And this is a good example of it. So the count set to 99. Will this ever execute? It won't. I don't know why you would set it up that way, but that's kind of on the programmer. It's different if like the user is inputting a piece of information and it never runs. That's different. But if you're the programmer, you intend it to run and it's not running, it's on you, right? Now that's a good thing for a programmer normally because you want to be in control of the code and what it does, right? This is important though. It says if the initial test is false, the statement's never run, right? So you have to make sure it's true. All right, so this is the one warning, and I think this is a good warning if you read through it. It says the loop control variable is modified in the loop's header. So here, right, this is the increment. It's a bad idea to also modify it in the loop body. Not a good idea. What is that going to do? Well, it's going to double increment it every time. Both increments will hit. Not probably what you want to do. Think about that. Well, there might be programmatic situations where you might want to do that, but no, not a good idea. Right? So bad idea is a good comment there. All right. So the other point, and here's the example of like, once again, like you don't have to always increment. What if you're counting down? Right. So like look at the second example first, right? Here we're starting with x at 10. And here we're saying as long as x is greater than or equal to 0, we're going to output it and then count down each time. This is a minus minus. So this will count down from 10, right, to 0 and then quit, right? And that's the decrement. That's pretty normal too, right? Here's maybe the weirder one, and one because we're usually in these spots going plus plus or minus minus. That's the more normal thing. But remember, this expression means x equals x minus 1. That's what it really means. So it is possible to use any of that kind of syntax here. So if I want to like increment by 2 each time, I can do that like this. I can just say plus equals 2. Or if I want to decrement by 2 each time, I would minus equals 2. Or optionally, you can go to the original thing that we saw, which is x equals x plus 2. Yeah, that would work too. You can have the whole expression in there. As long as it's changing x, it's fine, right? I know like this plus plussing, is that a word? I'm not really sure, right? But the grammar checker sure doesn't like it. All right. So the interesting thing is also as we're kind of playing with these, and I'll tell you what, these are actually two kind of fun ones to play with. You guys want to try those out? You're always welcome to do this, by the way. I think that you tend to see how code works better if you see it in action, right? So let's just run these two. And this generated a lot of output, right? The first one, what did the first one do? We start at 2, As long as X is less than or equal to 100, it outputs X, but we increment by 2 each time. So it's 2, 4, 6, 8, 10, all the way up to 100, and then it stops, right? The second loop, which starts here, starts at 10 and decrements, so it just counts down from 10. So just to show you, right? It's kind of fun. Kind of fun to see how code operates for programmers. All right. So back to this slide here. So it says for loops are really good for looping very specific amount of times. And this is why programmers like it, because they have control, generally speaking. What if, okay, here's the interesting challenge. What if we let the user determine the loop control variable? So for example, we'll ask how many squares, and then we grab that from the command line. And in fact, let's try this code because there's a fully built out example here. So let's do that prompt. And then when we get to the loop, we have this. And rather than like read the stuff off the slide, let's kind of figure it out from the code. So how many squares, right? And we can see how the loop is set up. So the number is preset to 0. As long as the number is less than max, what are we going to do? The square of the number is the number times the number. So, okay. And every time it will increment that number. We have no way of knowing what the user enters here. We know we're going to start squaring numbers at 0 and we're going to run up to here. So if the user enters like an insanely large number, this loop's going to run for a long time, I think. Right. You know what? Let's try it. Right. And sometimes I will tell you, sometimes it's fun to test code to see if you can break it, or see like how far it'll go before the computer freaks out or whatever. How many squares? Let's start with a really basic number. How about 10 squares? Right. So notice does the square of 0 is 0, 1 is 1, 4, 9, 16, it goes up to 81. Now what's happening, of course, is we never reach 10, but check it out. 0 to 9 is 10 values. Right? Because we started at 0, we're still getting 10 values in there. If I do use a much larger number, and so I'm going to push it a little bit, not too much, 1,000 of them, will this freak out? Yeah, now you start thinking about like the capacity of variables and stuff like that, right? We didn't exceed it, so I used the number I knew was safe. But yeah, I did 1,000 squares, and it shows you all the answers. Crazy. How long did that take? Second, 2 seconds. So it squared 1,000 numbers in a second or two. Right. Want to have fun with it? Like, hey, let's run it again. Hey, I could put the whole thing in a loop, right, to keep it running. How about 10,000 numbers? Okay, that took 3 seconds. And you can keep playing with that if you want to keep ramping it up. How about 999,999? That's a little more entertaining to watch. It's like you're watching a bad hacker movie or something, but you see it's like still going. That one's taking more than a few seconds. I'm waiting for it to choke and tell me you've exceeded the capacity of an integer, right? Which is, I think, where we're storing stuff, but maybe not. Maybe it's just doing the direct output and it doesn't matter. Yeah, there you go. What do you think, folks? Not too bad, right? Pretty impressive, actually, when you stop and think about that, because, man, even like putting that into a spreadsheet would take a whole lot longer than what I just did here, right? But pretty impressive, the number crunching capabilities. Okay, so wow, if I want a list of all the um, squares of all the numbers up to, basically, whatever, I could add a couple values to it so we hit 1 million even. We just watched it square almost 1 million numbers. That's insane, right? How long did that take? Not very long. right? Yeah. And the faster your processor, and your RAM and your CPU and all that stuff, the faster it goes. Pretty impressive stuff. But this is why we use software to crunch numbers. This is why we use software to process data, because the amount of time it took to do the math, that could be applied to any kind of situation, right? That would be repetitive. What I would hate to have to do, right, is to write code that would take every number from 0 to a million and write it line by line. I'd have to write a million lines of code. What we did here just iterated almost a million times in front of our eyes, and I think that's pretty profound when you start to put it into that kind of context. Programmers love for loops for this reason. Very, very easy to control. This is an example of a user controlled loop. We're giving the user the option to run it. One thing we didn't try though is, what if the user tries to break it? We didn't try that scenario, did we? Like we put in like -9. Okay, well, nothing happens. What happened? It just skipped over the loop. Right. I could write a loop that would check it, right, for invalid input, but we didn't do that. Right. So pretty fascinating though. And I love playing with like goofy little stuff like that, because I think it shows you a lot, frankly. All right. Let's take a look at this expression. And this is really kind of a unique feature. I will say right up front that not all programming languages support this feature. C# does. I think C, C++, and Java also do, but there's some C style languages that do not. And that is, we can actually have multiple statements that we're checking instead of just one, or multiple loop control variables. So in other words, here we're setting up an X and a Y. We're using the standard syntax for C#, right? You can do this, right? Separate them with commas. We're setting up an X at 1, a Y at 1, and then we're still checking one thing, right? As long as X is less than or equal to 5. And then we can increment both Y and X in combination. Notice the comma once again, not a semicolon, but a comma. And then we can do that too, right? And this would very simply do this. Let's drop that into Visual Studio also. Just run it. All right, so it just adds the numbers together, keeps incrementing both, and then eventually we get to 10. Pretty simple little program, but we can do that. So we can have two things. The truth though is, and I want you to think about this, we still only have one loop control variable, but we are setting two local variables right here, right? And we're incrementing two of them at the same time. All right. Now, normally I would say let's go ahead and do this little challenge thing. And I'm like really kind of wrestling in my head right now whether we should waste the time doing it, or would you guys find value in trying these? Okay. Alex, you seem like the only one that might be remotely interested right now. Everybody else is kind of giving me the blank stare. How about, you know what? This is actually good practice for the exercises. So maybe we should do this. I think this would be kind of fun. And I think that what would be kind of interesting about this is maybe just maybe, we could use different loop techniques to do each one. That would be one thing. Because I'll tell you what'll happen with me, right? If I code these, I pretty much go to the for loop immediately, and this kind of tells you something about, loop structures. Generally speaking, if I have a loop that's going to do something very specific, the for loop is exactly what I go for. And these are, to me, three scenarios of very specific things that need to happen. So I would go directly to a for loop. I wouldn't even bother with a while or a do while. Right. Now, if the try it was set up a thing that asks the user for input, and then if it's invalid, have them enter it again. I mean, that's a while loop for sure. Right. And all right. So how about let's try at least one of them, right? How about create a loop that displays the even numbers between 2 and 10, including 2 and 10. We just kind of did that, didn't we? All right. So I'm gonna take that directive here and paste it in. And let me see if I can just re-engineer the loop that I have. All right. And I'm not going to do multiple statements here, I don't think. All right. We wanted to display the even numbers between 2 and 10. So can I start my x at 2? Sure, why not, right? And then I can just right line x. So start at 2. And then every time it goes through, how much should I increment it? Well, you know what? That sounds like the scenario for plus equals 2, right? So we're going to add 2 each time we go through. And then what's our logic test? We want it to stop at 10, but not exceed it. We want it to include 10. So this should work. Let's try that. 2, 4, 6, 8, 10. It includes 2 and 10. See how simple that was? If I was to do this with a while loop, how would I do it? Well, that's an interesting question, right? Here, I'll just create a while loop here to have you think about it. And really what I would do in this circumstance is I'll create a new variable and say int y equals 2. So I'd have to set it before. Then I would do my logic test, which is while x is less than or equal to 10, then curlies, and then I would just right line the same thing, obviously. And then I would want to increment. I know it's not like Visual Studio is trying to get me to go y plus plus. Wrong answer, by the way, right? We want to increment by 2 each time. So I want a plus equals 2. Oh, yeah, and I'm using X. Duh. Sorry. Teachers make mistakes too. Except mine don't count for a grade. I've already gone through that. Right. All right. So here's the while loop version of it. And you know what? Let's comment out the for loop version. So now just the while will work. Same output. So I think this is a nice little example of I can accomplish it with any loop style, really, right? And I could switch it to a do while and still make it do the same action. But I think there's a really strong takeaway, and I want you guys to internalize this a little bit. There's a reason why programmers almost always go for the for loop first, because to me, the declaration of it alone makes it a little bit simpler, right? If we try this challenge, create a loop that displays all the numbers between 11 and 34, including 11 and 34, right? So I'll just put that challenge here. And now you know what? I won't get rid of the while loop. We can leave it there. Just comment it out. We'll use our CSS style commenting. And then we'll move this closing comment markup here. So now the for loop is active again. We're going to start at 11. Could I just switch this to 11? Yes. How long will it run? Up to 34, including 34. The other way, another thought on this is some people would do this. It'll never reach 35, right? But it'll reach 34, just to show you that that can work. And then it says all numbers. Excuse me. Very bad. Sneezed into my hand, by the way. Not good. We're incrementing 1 each time. And here goes the run. There it is. Very, very exciting. 11 through 34. what's the last challenge? Create a loop that displays all the numbers between 56 and 3 inclusive, counting backwards. We haven't tried that one. Let's try that. Okay. All right, so coach me here. What should I put in this first position? What do you think should go there? If you're thinking or about to say 56, you're correct. That's a good number to start with, right? And because we're going to count down from it, so we may as well start with that value. Now, we're still going to check X, but we're going to flip the sign here, right? So we're going to say as long as X is greater than what? Would that work? Or will I exclude something? This we already know is going to be a minus minus, right? It's going to decrement. Will this display 3? No, it will not. So we have to include 3. You guys notice my bad syntax here? Put the equal sign before. Yeah. That's why on-the-fly debuggers are so wonderful, by the way, because it catches their mistakes as we're making them, as opposed to when we try to run the code. So let's see if that worked. There it is. Did it start at 56? It sure did. And it counted all the way down to 3. So there's your example. Let's try it. Hopefully you get a little bit of value out of doing that. I think that they're kind of like mini assignments, right? They're kind of almost like Codios or something, right? But you know what? Real frankly, whenever you guys are like reading through materials like this, I think it's really important to try the code, right? To see how it goes. And then you get a feel for it. And then when you get like challenged with a real situation, then you know how to flow with it. Now, let's take a look at this next section here of the PowerPoint, which starts talking about, you know, in a way, some sample situations that might be common in programming, right? And they totally are, right? So for this slide here, it says a sales total program. We need a program to track total sales. So every time a salesperson makes a sale, they enter each sale into the system, into the program. When they are done entering the sales figures, the program calculates the total, right? So first of all, we have a couple questions, and it is how do we store the sales amounts to get the total? And then how does the salesperson indicate they're done entering the sales? Okay, this is a couple of things. So we're going to continuously prompt somebody for information, store that information, keep adding that to the value, right? Because if they make a $10 sale and then a $20 sale, that should say 30, right? So we're accumulating those totals. And then we need to give them a way to exit out of the loop when they're done entering the information. Okay, well, if it's a 7-day thing, we could set a for loop and then that would terminate, right? But yeah, we're going to actually have to keep a running total, right? So it says running totals need 2 things, a loop to read the sales amounts and a variable to accumulate, and that's a keyword here, the total, all the amounts, total all together. And so we create a special type of variable called an accumulator. Now, in terms of like how it looks in code, it's not like anything more special. You know, we just, you know, something that's going to continuously be added to, we think of it as an accumulator. It's an accumulator thing. We'll start it at 0. Every sale that we grab will get added to it. It will accumulate in the total. Here's the kind of the pseudo code or the flow chart for it, right? We'll initialize the accumulator to 0. We will test, are there more sales? Yes. Okay, if there's more sales, that's true. Then we'll read in the next amount, add that amount to the accumulator and ask again, are there more sales? Yes, right? So you want to keep answering yes to this, obviously. And then when you get to the point where you have no more to enter, then you hit no or type no or whatever, and you're out, right? So what is our loop control variable here? Well, it's going to be user defined, basically. That's the point. And so here's a sample. First, we take our total, right, which can start at 0. We're going to set up a thing right here. So we're going to say sale number equals 0. Okay. And then as long as that sale number is less than 5, we're going to keep prompting. So we're going to prompt her, enter the sale amount, and then we're going to keep adding it. So what's going to happen here exactly? No, you know what? Let's run it. I'm a big fan of doing that. If you guys haven't noticed, let's run the code to see what it does. Let's just blow away all this stuff here. Paste in the fresh code. So let's hit the run button. Enter the sale amount. I'm just going to use small numbers, 10, 20, 30, 40, 50, and I did 5 on purpose, right? And they kind of counted up to like 1, 2, 3, 4, 5, basically. Because I knew this was going to run 5 times. How do I know that? Because I could tell by the for loop. The for loop's designed to run 5 times. So what if I had another value to enter? That doesn't really meet the criteria, does it? Right. This is a finite number. So if I ran a business Monday through Friday, this would work fine, right? If I ran a business that was also open Saturday, well, now I got a problem, right? And that's kind of where they're leading us to here, by the way. And here comes that other terminology here. All right, so a sentinel value, this is where we allow the user to enter as many amounts as they want. So loop that'll just keep running. And how do you signal to the program that you're done, right? A sentinel value is chosen because it can't be a real value. So for example, they might make sales of 97 and 85, and then to exit out, they enter in a -1 because that can't be a sale, right? And then that's the value that pops us out, right? So looking for a specific value that would terminate the loop is called a sentinel value. All right, so when it counters the sentinel value at exit, good sentinel values will depend on the program and how it's coded. For example, for sales, it makes sense that maybe you had a sale of 0. I don't know why you would enter one that is 0, right? Why would you? It wouldn't change total. Or -1. Those would be real logical ones because you can't really kind of do that, right? Now, notice it says it's important not to add the sentinel value into the accumulator. So you have to also accommodate for that as you write your code, right? So if I'm looking for 0 or -1, I don't want those values affecting my balance, right? Because if I add -1 to the accumulator, it reduces the sale amount, so it's incorrect. Maybe 0 would be better. I'm not really sure. All right. Next thing you have to ask yourself is what kind of loop do you use? And, I've kind of told you, like, from the standpoint of a programmer, programmers tend to prefer for loops, but they don't always work well with user interaction, by the way. I think in this scenario, a while loop is probably wiser for a number of different reasons. All right, so it says, consider what happens if the salesperson's had no sales and they enter -1 for the priming read. So we prompt them, right? And then they type in -1 and it goes into the amount. Okay, not good, right? Because now, we have a negative amount that we're dealing with. However, it says it's also helpful to tell the user what the sentinel value is. So if you noticed here in the prompt, enter amount or enter -1 to exit, right? So you should let them know in advance what that's going to be. So as long as the amount is not -1, we will take the amount and add it to the total. And then we will prompt them again to give them a chance to do it. All right, so let's give this a try. So here I am copying the code again, taking it into Visual Studio and pasting it in. So here's our priming read. And I'm going to go to the next slide to grab this code, which I'll also paste in. So presetting the total to 0, we give them a prompt. We read in the information into amount, And as long as that is not -1, the loop will operate, add it to the amount, prompt them again, grab the value, check it again, and just keep going. And then when we're all done, which is when we enter -1, then we will see the total. Okay, so let's watch this happen. So this is a really good example of a sentinel value and a bunch of other concepts, really. All right, let's put in some numbers. So here's 20, 30, 40, 50, 10, -1. We already know the answer to this one because we just did it. The output should be 150, right? What if we run it again and we just start with, I don't know, -10? Oh, wait, it took it. That's not quite the same, right? Okay, well, now we have a negative balance here, don't we? No, not quite, but it does. So a negative number other than -1 would be problematic. But you could also say maybe that's a return. Right? Maybe 0 is a better sentinel value. I'm not really sure, but generally speaking, we could write code that would disallow a -1. You know, if you think about like some of the other code that we looked at, we don't want to get that deep here, but this is an example of allowing the user to basically enter a bunch of numbers. And you see, I'm just kind of like oofly adding a bunch of numbers and then type -1. Kind of cool, right? Here's our first example of like the user's in control of when the program ends. You know, so this is very, very useful. And at the same time kind of pragmatic at the same time. So that was the sales total program. So now we got another try it challenge here. So let's see if we can kind of do this one. It says write a program that repeatedly asks the user for a number until they enter. Well, we already did that, I guess. Right? Am I correct? We just already did that, so why do it again? When the user is done, display the total and average of all the numbers that were entered. Okay, well, this is a different scenario. But correct me if I'm wrong, could we not use the same loop to build this? And it says, make sure do not include the sentinel value of -1 in the total and average calculations. All right, let's try this. Let's see if we can alter our code to allow for that to happen. And I don't think we need to change the total or the prompts. I think those are all fine, right? Will we still need to add the amount to the total? Yeah, right. I mean, if we're going to do an average, right? What does it? Okay, so here's a good question. What does it take to determine an average?
You need a count of how many things you're averaging.
Yeah, right. So I have to take the total of all the things added that were entered and add them together, and then divide it by the count of the number of things that were entered. Okay, so maybe we need a counter up here. So let's create another variable and let's call it count. Right? Let's set that to 0. Right? And this will be our counter. We're also going to calculate an average, right? Well, okay, so let's talk about that for a second. If I'm inputting nothing but integers, will my average also be an integer? No, not necessarily. It could end up being a fractional value. So I'm just going to create a double called average. I am going to preset it to 0 on purpose. Why? Well, what if the user doesn't enter anything? Right? We don't want it, to have no value. We'll hold the average. We'll prompt the user as we've been doing. We'll have that priming read. We'll do the same check going in. Any amount that's entered will be added to the total. Is that correct? Yeah, no, you should scratch your head on this. Well, if they enter -1, think about this. If they enter -1, they're never going to reach this code. Right. So that already excludes that from happening. Right. So that we're safe in that regard. But every time we step through here, we do need to increment the count. So we're going to do count plus plus. So we'll add to the count. Right. They'll keep adding values and numbers. Eventually, they're going to add, they're going to type -1 to stop. And then we exit out. And we don't want the console to do right. Actually, at this point, we want to do some math, right? So we will say average, and isn't this beautiful? It comes up with the exact right equation for us. Thank you. Microsoft AI or whatever is, it's really what it is. It's very good intelligence. It's not really AI. It appears to be AI, and it's correct, right? So we're going to take the total and divide it by the count, and then we'll have an average, and then we can say, well, we can do two things. So total, we can display the total. I think that would be actually helpful to see it. And then we can have two more statements. One would be for the count. So we can say count. And then split count. And then here we can put average and display the average. Seems pretty reasonable, right? Straight ahead. All right, let's give this a try. And you know what? This is me being kind of the neat freak. I want my stuff to line up. So that's me. Okay, you guys don't have to do that. Right? A very primitive way to make it all line up, but I think it will look nicer this way. All right, so here goes. Let's run it. And whatever you put in here, by the way, you should know what the results are accurately in order to determine what the output should be. But let's just use some really simple numbers to start with. So I'm just going to put in 1, 2, 3, 4, 5. Okay, so what's the total of all those numbers? Quick, 15, right? You got that? Right. What's the average of all those numbers? It's a really easy answer. Yeah, if you're actually doing the math, these are sequential numbers. The middle number is the average. Right, 3. Right. I don't even have to do the math because they're in sequence. All right. So now when I press enter, I should see total 15, count is 5, average is 3. Oh wait, I gotta exit the loop. Pretty slick, right? I mean, not super slick, but it's kind of neat because I could run this as long as I want with as many numbers as I want, and it will give me the average. That's pretty useful. And I can do it really, really fast. So this is a good, for a very primitive little program, it really is a pretty useful little program. So if you had this loaded up as an executable on a system, you could bring up a prompt and just type in 10 numbers really quick. Well, you know what? I can do that with Excel too, by the way. Right? If you guys aren't familiar with doing that kind of stuff in Excel, right? And I'm just going to show you this because a lot of people just really are not aware of okay. So take a look at how Excel operates, and it gives you kind of a little bit of a clue as to what's going on behind the scenes with a product like this. But I can take the same numbers and type them in, not even in the same order. In Excel, all I have to do is highlight the numbers, and it tells me the average, the count, and the sum right down here. Those are so common that the spreadsheet does it automatically. Pretty slick also. All right. Excel is a wonderful product for coders, and the one tip, and if we were like in advanced classes together, I would like totally hammer you guys on this. But whenever you're doing math in a computer program and you're expecting to have accurate results, you need tools to test the results before you can ensure that your program is doing it correctly, right? And so when I'm often teaching like my data analytics courses, this is the thing that I'm, I tell people, hey, you're writing like Python code or whatever kind of code that's importing all this data, processing it, and giving you all these results. Is it correct? How do you know? Well, you need a different tool to do it. If you're doing really simple things like sums, averages, and counts, well, you see how easy Excel does that. But if you were doing something more complicated, I might go as far as setting up complicated formulas in Excel to validate what my programming code is doing, right? Just to make sure that the output I'm getting from my software is correct. Excel is a really useful tool in that regard, and I use it all the time when I'm programming to validate mathematical operations. Really, really useful, by the way. So if you don't have, access to Microsoft Office, of course you do as a student, but let's say you're a private citizen and you don't have access to it, because basically you don't want to pay Microsoft for it. You can use, there's free tools that often are available. Google Sheets is a really good one. And then if you're on a Mac platform, you can use the Numbers program, which is their spreadsheet. And then there's all these open office variants that are basically clones of Excel anyhow that you can use to do very much the same work. But I find that's a very helpful little thing to do, by the way. Now, since we finished that slide, we've reached a really good pause point again. So we're going to take another 5-minute break, folks. So we'll come back at like 9:06, and we should be able to finish the rest of the PowerPoint in the next segment. So I'll see you guys in about 5 minutes. All right, our next topic tonight is talking about nested loops, and that, in a microcosm is basically when you put a loop inside of other loops, and that's kind of mind-boggling when you first start to learn loops. That wait a second, I can do that. I can put a loop inside of another loop. Yes, you can. Just like you can put an if statement inside of another if statement, and when they're put inside of each other, we call them nested loops. And we use the analogy here to kind of get the point across of using a clock as a really good example. And it's a good example for a number of different reasons, because when we use a clock, operates in a loop anyhow, right? It spins. We have these arms on the clock that spin around. And okay, so let's just follow through the logic here. It says, think of a clock. The hour is 1. The minutes run from 0 to 59. Then the hour goes up to 2, right? The minutes from 0 to 59 again, and then the hour goes up to 3. And so like what we're really seeing is that there's one loop that's running the minutes and another loop that's running the clock, right? And then if this cycle continues, it just keeps counting up, and it keeps going basically until it gets up to 12, and then it starts over again, right? And so it says, the question is, how do we implement minutes going from 0 to 59? Well, a for loop is a really good mechanism. So we can set minutes to 0. And as long as minutes are less than 60, we can keep incrementing, and it will just increment. Okay. That would be one example. Now, it says here next that the loop to control the minutes should repeat. How? Put that loop in another loop. How many times do we want the minutes or loop to repeat? Well, every iteration is 1 hour's worth of minutes. So it depends on how many hours we want. Right. So here, let's take a look at an example of a nested loop then with a clock. So the inner loop is going to operate for so this inner loop, which we just kind of thought through a couple slides ago, is going to operate in its entirety every time the outer loop operates once, right? So when the hour is 0, so we're at midnight basically, we will start there at midnight. We'll come down here, we'll run 60 minutes. When that's done, then the hour is 1. Then we come down here, run 60 more minutes, come back up the hours 2. And we keep going until we reach 24. And then basically we have a day, right? So this is a really good example of the inner loop will execute all of its iterations in a single iteration of the outer loop. That's how it works. So I run the outer loop. When I encounter an inner loop, it runs through its entire course, and then it goes back to the outer loop to run its next iteration. So hopefully that's pretty clear how that works. Right? Not to repeat myself, but right, the inner loop goes through all of its iterations for each iteration of the outer loop, just to kind of reinforce it. How many iterations total? Well, per that code that we saw, we can actually figure it out. We can see how many iterations total are happening. So the inner loop is going to operate 60 times for each one of these. 24 times 60 is 1,440 iterations if you're counting, by the way. Right. And it says, be sure to use different loop control variables for the outer and inner loops. And in that scenario, we did use hours out here and minutes in here. But sometimes when you're doing this type of thing, real frankly, you use like generic things like X or Y. And sometimes you make a mistake and use the same ones, and just be careful with that. Don't do that, basically. So make sure to use different loop control variables for the inner and outer loops. Don't use the same ones. You will have all sorts of problems if you do. Now, real common usage for doing nested loops is when we start to work with multi-dimensional structures. Rows and columns are basically a two-dimensional structure. So when we think of like a spreadsheet, like when we just looked at Excel, and you see how this all ties together, right? That's a two-dimensional structure. We have rows that go across and columns that go down, and we form kind of like a matrix basically. So it says a common use for nested loops is to print a table. First, we start a row, we print column 1, 2, 3, etc. Then we start another row, print the same columns, and another row, print the same columns. And you see when it's kind of repetitive. And a really good example of that is a multiplication table, right? So we have, and excluding kind of like the marker rows and columns on the outside, if we were to do a multiplication table, we could have 2 separate loops that basically have their own values that they're incrementing through. And for each iteration, we feed in all these values. And then as we kind of come and do the math, basically, with each iteration, we can output the contents of each row and column. I think it's really pretty fascinating because it is kind of a logical process like that. And a loop really kind of lends itself pretty well to that. So what would that look like here, right? So, for example, if we had a couple of constants here set up for rows and columns, each set to 4, right? What would this create? Well, you know what? I think that the best way to do this, right, is to kind of, once again, drop it into Visual Studio and take a look. So here's the code. So we set up rows, columns, and I know we didn't do a lot of this, but whenever you set up a constant, right, this is the keyword that you use in front. That means it's a variable that cannot change, right? And the convention when you name a constant is to use all uppercase letters, by the way. So in this case, we start with row 1. We'll run from 1 up to 4, incrementing each time. For each iteration of the outer loop, we will completely iterate through the inner loop. The inner loop will basically run from 1 up to 4, again, incrementing 1 each time. And each time it will multiply through whatever the current value for row is and the current value for column is from each loop, and then a space in between. All right, let's run this and see what it does. Here's the run. Even though it's primitive, it is forming rows and columns of a multiplication table, just the first 4 values in each direction. I could very easily ramp this up and do the whole multiplication table, right? What would that look like? Well, I would just simply increase the numbers to 10 or whatever I want, right? I mean, so like when you're a kid, right, this is like a thing that you're supposed to memorize, the multiplication table, but usually it's only, up to 10 times 10 or 12 times 12, and that's about where we stop, right? Because then it gets too complicated to remember. But if you have like those basics, here's a way to generate a multiplication table. If I wanted to change this, right, and I want to make this 10 times 10, I would just change these two values and I would just run it again. Now the output won't be quite as pretty. Part of that is because we're only printing one space in between, but I could increase that. I could also run, and think about this, conditional code that checks that if it's a certain value, add two spaces. If it's a different value, add one space, for example, right? So you can make a actually very pretty looking output. But here's the multiplication table. Not perfect, but it, at least in visual appeal, but numerically it's correct. Pretty interesting little program, right? And it's all done basically, really, one multiplication is happening. Isn't that clever? Right? Because it's a repeated action, but it's being repeated on the rows and the columns. So all of the interior stuff happens first, right? So the columns, so we're on the first row and we go all the way across. And then we go to the next row, go all the way across, and then keep proceeding in that fashion. Nested loops are just perfect for doing this, right? If you want to try something really goofy, try writing loops that do this, pattern A or pattern B. Right? Want to give this a try? you know, um, maybe these are a little bit challenging, but how would I do something like that? Even conceptually, how would I do this? Well, the first row only iterates once. The second row iterates twice, right? We could easily write the code for this. I kind of don't want to spend the time on it right now, but this is just kind of a pattern thing. So instead of, um, outputting math here, what would I output? Yeah, I would just output that, like if I'm outputting an asterisk, right, I would just output an asterisk. Right? Okay, let's run this. This isn't going to do exactly, no, that creates a square. That's not what we want, right? So we would have to like write logic here that would kind of work with that. So how do I get it the first time to only output once? Yeah, this is where it gets a little funky, right? So we do want it to run 10 rows, right? If you go back to the PowerPoint, so it's 1, 2, 3, 4, 5, 6, okay, 7 rows. All right, so we can change the rows to 7. What's the number of columns? Well, you know what? That depends. There's your answer, right? So, do I want to preset columns to a certain value? The outer loop will be fine. It'll run 7 times, and I can prove that. I can just run it now. So here it is. There it is, 7 times. 1, 2, 3, 4, 5, 6, 7. That's 7. But the first time we run through it, we want it to only output once, right? So the first iteration, what should be the logic that changes here to make that happen? Well, this will only run up to whatever. Would this work? It's okay to yell at me if I'm not doing it right. Think about this. Would this be a loop inside of a loop? Let's ask that question first. Okay, I'm going to contend that we need something else to work with here. So we have a constant up there. Should we have maybe a variable, an integer called count? Maybe we can preset that to 1. And then here, the column will start at position 1, but as long as column is less than or equal to count, would that work? And then do we want to increment columns or count? Alex, I see you like mumbling something there. So maybe you're onto it. All right. Well, that gives me 1 star, but that's different than what we had before, at least, right? So what would have to happen here? Yeah, you guys can really kind of think this one through quite a bit. There's okay, the thing that we're incrementing is still columns, right? We want to increment the number of columns, but we want to output more each time. So how would we do that? Yeah, you guys ruminate on that for a little bit. Interesting little solution. These are very, very common programming exercises, by the way. And I'm just going to kind of give you fair warning. When you guys learn another language here at school, let's say like you learn Python and they teach you loops, they might make you do the exact same exercises, but in that language, right? And so that's why I'm kind of like seeing if anybody's got kind of like a solution here. Would a for loop inside a for loop be right? John, go ahead.
Can you change it to a do while and you want to execute the do while your columns equal count?
Oh, your columns equal count. Okay, so you guys hear John's question, right? All right. Why would I want to switch to a different loop structure?
Well, you want to execute it until you get the right number of columns. You want one first, and then you want to increment. So you want to increment and execute the number of columns you have.
So you're contending that I should do a do, and then I want to output the asterisks. I think we're just missing a piece of logic, right? So what's the truth statement here then?
You want your columns to increase by 1.
Well, we want the columns to increase by 1. I'm letting you think on this a little bit, John.
Yeah, I've got it wrong.
You know, the best way to figure it out is to test it, right? Like if I try running this, what happens? Yeah, this is an infinite loop. This is kind of interesting. Yeah. It's kind of interesting to watch. I don't know how that's traveling over Zoom, but yeah, Control C on this one for sure. I'm going to contend that we can go back to what we had and see how I Control Z'd my way out of that problematic situation. Just kept hitting Control Z until it was back to where I was. So every time we go through, we're going to output an asterisk, but isn't it conditional? And we're just gonna write 1. So the first time through, we come to the inner loop and we output this once. How on earth do I get this to multiply? How do I get it to do multiple times? The first time is going to be once. Second time is going to be twice. And all of you guys are hanging in quiet desperation here, hoping that I'm going to like answer the question for you. I'm going to have you ruminate on this a little bit. The problem solving here is kind of a combination of different things because we're doing like we're using like weird terminology that maybe we shouldn't use. Rows and columns might not be the best thing, but for row 1 we're going to output it once. So as long as this is less than count is going to start where am I? Well, count starts at 1, right? So the first time it'll be 1. I'm never changing count. That's the answer. So if I take count and I increment it each time, Now what happens? Oh, same thing. Got an infinite loop, right? So maybe that's not ideal. Is count what I want to increment here? I mean, the first time, if I leave this out, it's just going to print one asterisk each time. Do I need a different variable? Do I need a different value? Do I need a different increment? The column count's going to increase each time.
Isn't the check backwards though? Wouldn't it be count less than or equal to the number of columns?
Okay, so now now John, you're starting to think like a programmer, and I love it. Because you're thinking about it, and I appreciate that. So we're gonna say as long as the count is less than or equal to the number of
Your constant columns.
oh, you're talking about the 10 up here,
Yeah.
or this one.
You want to count up to the number of columns.
All right. Well, why don't I just hard code a 10 in there?
That works.
Okay.
It'll give you
And then am I checking the right thing then? Do I need to check this at all? Can I just do that? I mean, yeah, I could hard code the constant value here. So maybe I should do that. Maybe we just go cols. Right. That's basically 10. Let's try that. Not so much. I like your line of thinking though. But isn't this the first thing we tried? It is. Yeah. Nobody's got a solution on this one. You guys, I know I have some experienced coders in here. Nobody's got a hack for this. It's not really a hack. Maybe we should let this one hang here for a little while because I love when you get like programming things and everybody's like, oh, I don't know. All right. So the first time through, right, we get a whole row of what? Well, we are running this thing. I'm not really sure that that's what we want. Maybe, and I'm just kind of putting it out there. We are running up to count. So I'm just going to run this once. What happens here? Okay, it just does it once. All right. So we successfully made it run once. Maybe count gets incremented in the outer loop. Well, you guys didn't think about that, right? All right, let's try that. So in the outer loop, and where do we do that? After the right line? Sure. Just so count plus plus. Wow. And see, this is the crazy thing about this logic, right? You can look at it and it just doesn't resonate like where you need to put the change in the code to make it execute, because this is always going to stay the same. If I increment it internally, then we get an infinite loop. But if I increment it external, then the next time it runs, it will be one higher. So this is a really clever but simple little program. Now, if you wanted, and I don't want to really spend the time on this once again, so that we were able to do this pattern. That wasn't too hard. Right? Well, it took us a little while, but it wasn't that hard. Then we could do this pattern, but this one's a little different. So the first time it is a hash mark. The next time it's a space and a hash mark. And really, it's the number of spaces that are repeating. So is this, okay, so I'll tell you what the answer to this one is. The hash mark would print in the outer loop at the end. The spaces would print in the inner loop and an increment in the same way we did the asterisks. So the inner loop would add the spaces. And I don't know if you're really catching this here, but maybe there's a space here even. But yeah, the inner loop would add the spaces. The outer loop would add the hash marks. That's how you would accomplish that. And these are really goofy little things. But if you play with this, so we already did, I kind of did this one, but if you play with this a lot, I mean, it really challenges the way that you think. And I love it just for that reason. And maybe you guys are like this. Maybe you guys are like puzzle people, like like you like to play Wordle or or whatever, like crossword puzzles or whatever. But it's kind of the mindset you have to go into to figure this stuff out. And you know what? There's no harm done in trying it, right? And so, John, you were throwing ideas out there. I love it. You should throw ideas out there and try them and see, like, oh, well, this did that, so that's not right. Let's try this. Oh, that seemed to work. Now, I mean, I know maybe I let it hang there for a little too long, but I don't think you guys would have seen this initially. An experienced programmer would catch it right away, right? Because of the output that it's generating. But the solution is actually very simple and it's pretty elegant, actually, right? Okay, another thing you're going to ask yourself, and this should be a natural question, is like, all right, well, we just used loops to kind of control things in 2 dimensions, right? Across and down. Could I nest another loop inside the inner loop? Sure, right? If you use the clock example, let's go to the clock. The clock's got hours and minutes. We didn't do seconds, but the seconds would be just like the minutes, right? All right, and could we put another loop inside of there? Sure, because there's milliseconds inside of a second. So there's another loop. And we could just keep breaking it down. The difficulty for us as human beings is keeping the conception straight in our head as we're coding it. When we look at, and this is one of the reasons why we do like 2-dimensional output, rows and columns, because you can easily see it on a screen or on a piece of paper. When you start to add in that 3rd level or 4th level or beyond, the computer doesn't freak out. We freak out because conceptually it makes no sense to us. But I like the clock scenario because it shows you that I can take an hour and break it into minutes, into seconds, into milliseconds, and then I can even go deeper, or I can go the other direction, and a day fits into a loop of 365, right? That fits into a loop of like whatever. You can just kind of like take it in either direction. The conception, once again, is more the challenge than anything else. Right. Let's move on to the last concept here so we can round out the evening. And I love these historical computing images. They're wonderful. All right. So let's take a look at this next concept here, which is the break statement. And we've already experienced in the switch statements when we do, a switch and we have a case and it hits that particular case. At the end of the code block inside the case statement, you have to put a break statement to jump out of the case and move on so you can process other code, right? And the point was that basically wherever that break statement is, you are jumping out of the code. You can also use break statements in the body of a loop, right? So you can set up scenarios to make a loop terminate basically at a point where you determine that it should exit, right? And it could be conditional, basically, is the point, right? So let's just check out this little example here. It says generate random numbers between 0 and 1 forever. Okay, that's kind of a long time. Count how many numbers you've generated, right? If a random number is less than 0.1, then stop. So here's the question. Will this operate really forever? No, logic would dictate that 10% of the time we would hit a value in that range. So there's a 10% chance that the loop will terminate with every iteration of the code. That's kind of the point. So more likely than not, eventually it will, it might run for a long time, but eventually it will hit that 10% and terminate. We wish, our luck was that good for the lottery, right? Yeah, not so much. All right. So here's a little block of code, and it is pulling in the random number generator here. And I think this would be kind of fun to run this one. Let's go ahead and do that. Visual Studio, let's paste it in. Set up a counter at 0. Real interesting technique here, right? Here we have a while loop, and the Boolean test we're doing is hard coded to true. So what's going to happen with this loop? It's going to just run, right? Very, very common technique, by the way, in programming. The only way to break out of this loop is if that random number ends up being in this range, less than 0.1, then it will break out. And then each time it will do a count, and then we'll see how many times it took before it jumped out. Right. So let's try this. I think this is a really fascinating little example. Okay, twice. All right, let's do it again. 28 times. Pretty interesting. Do it again. 3 times. Again. 4 times. Again. 16. All right. So you can see it varies, right? But on average, if you like average this out, how many times did it take before it hits? That's a pretty easy answer. 10 times normally, somewhere in that range. But it could hit the first time. It could take a while. What was the highest one we got? Like 28, right? But here's an example. If I remove this, what will happen? If there's no break, this loop will run forever, for sure. Right. So kind of a weird technique to hard code true there, but you know what? Sometimes we do that, right? And the reason we do that is because we are setting up logic inside the loop to allow us to exit. The break statement is the exit point. Yes, I could put more code with the if statement, right? But you know, this is just a primitive example. It's a good way to look at it. There's also a different scenario, right? There's the continue state. So break pops this out, continue causes the loop to exit early. So same kind of thing. Now, check this out though. This is a little bit of a difference. Break makes the loop quit altogether. So whatever loop you're in, you are out. It's done, right? No more iterations. Doesn't even finish where you left off. So for example, in this code, once we hit break, that last increment never happens. All right. Difference with the continue, it ends only the current iteration. So the current loop through would change things. So, all right, let's try this little scenario here. So it says the randomness tester version 2. So now we're going to generate 100 numbers between 0 and 1. And then we're going to count how many of them are greater than 0.1. Probability says it should be 90%, right? I mean, it's kind of a no-brainer. If you run it enough times, it should be 90%. Here's the code. Okay. All right. Let's pull that into Visual Studio and test it. Let's take a look at the setup first before we run it. So we got the for loop set up. We have a counter of, well, actually we have an index variable of I set to 0. As long as I is less than 100, we're going to run this. We're going to generate a random number. And if the random number is less than 10, we will skip the code below this loop. Now, what is the point of what they're doing here? Okay, so when will the counter hit? When the number is greater than or equal to 0.1. So 90% of the time, the counter will hit. 10% of the time, it won't. And then we'll look at the count. All right, let's just run this and you'll see what I'm talking about. 86. Okay, so what is the ideal output we're looking for here? The ideal output would be 90. Right? And this is where it gets a little weird, right? Because like all things that seem to be random, often they're not quite, you know. And in order to come to like the consensus of like, you know, probability is based on mathematical potential, but in actuality, right? So, for example, like if I'm rolling dice, what's the probability that I'm going to roll snake eyes? Well, you'd have to know the total number of probabilities of rolling that, right? It's a 1 in 6 chance on each dice, you know, and that 1 in 6 chance multiplied out is one chance in 36, basically. 1 in 36 chance that I will roll snake eyes on a pair of dice. Now, I could roll dice 36 times and never get snake eyes, right? What this is telling us is that every time I run it, it should get really close to 90, right? On a rare occasion, it will be exactly 90. If I ran this 1,000 times or 1,000,000 times and then averaged all of those values, it should be 90 or almost exactly that. But here's the problem with probability is we really don't know. If it's truly random, I might roll the dice 1,000 times and never hit snake eyes. It's unlikely, but it's possible, right? So then when you look at the probability of winning the lottery and it's like one chance in like 50 billion or something insane like that, it's like, why are you throwing your money at the lottery is kind of what you, the conclusion you come to. But you know what? We all still do it, right? Because if it just happens to hit, then we're all set, right? Then you don't have to learn how to code to make money, right? You just take your lottery winning song and call it a night. Folks, that's all we have for tonight. So we've got through all the material. Um, you know, the break and continue statements are kind of weird ones, but very useful ones. This one allows the code to keep running, and we use it to demonstrate a couple of key concepts. Now, we do still have 8 minutes left during class here. I am going to end this recording, so this recording ends here.